So in general, energy, kinetic energy, can be transferred both in and out of a system. And if energy is being transferred, it's going to be transferred through particle collisions. So in order for energy to be transferred from one substance to another, particle collisions have to occur. So particles collide, then they can transfer energy, then they can change their state, or they can change their speed, or whatever that energy is being used for. For right now, to help us keep track of where our energy is going and what it's being used for, we're going to use our LOL diagrams. Hopefully you remember these from physics. So we're going to use, you might have also heard of these called energy bar charts. If not, we're going to walk through them a little bit. Basically, our first L, our first graph, is kind of our picture of our before, what's our energy being used for at the beginning of a situation. The last L is our after picture, so at the end of something happening, what's our energy look like? And then our circle in the middle, that's representing our system. So we're going to use that to show whether the energy is coming into the system or whether the energy is leaving the system. So let's walk through a couple of examples. Okay, our first example says a cup of coffee or a cup of hot tea cools as it sits on the table. So we're going to analyze two different things here. We're going to analyze what state of matter it's in, or what phase it's in, the tea is in, and then we're also going to analyze how its thermal energy is changing. Okay, so first of all, let's look at phase energy, just because that's the easiest. What state of matter is hot tea? It's a liquid. Liquids, we know, have moderate phase energy. So I'm going to draw the phase energy bar up to the middle line. Now, as the tea is cooling, you should be asking yourself, is it changing states? No, it's still a liquid, it's still tea. So it's still going to have moderate phase energy. Now, in the before picture, it's hot. Since the tea is hot, that means it has a high amount of thermal energy. So I'm going to draw lots of thermal energy. And then it says that, our situation says that it cools as it sits on the table. Let's assume it sits there for a long time, and it is very cold by the time that you actually get around to drinking it. So we're going to say that since it's cold, it has low thermal energy. Now, if we think of these in terms of boxes, our phase energy had 2 at the beginning. Since our phase didn't change, it still has 2 bars of energy at the end. Our thermal energy had 3 at the beginning, because it was really hot. It had high thermal energy. At the beginning. At the end, since it got cold, it only has 1. This means that, how many did we lose? We lost 2 bars of energy. So there's 1, there's 2. And you should be asking yourself, did it come into the system, did it get added, or did it leave? Well, we went from 5 total to 3 total after, so that meant that it left our system. So our energy, in the form of thermal energy, left our system. Okay, let's look at a second example. So in this one, it says a tray of water at 0 degrees Celsius freezes. Okay, so let's analyze our phase energy first. So we're going to assume, since it's going through the process of freezing, that means it has to go from a liquid to a solid. So we're going to assume that it's a liquid first. So it's going to have 2 bars of phase energy. And since it's freezing, we know that it's going to a solid. So we're going to say that it has only 1 bar of phase energy, because we know that a solid has less phase energy than a liquid. So we're going from 2 to 1. Now our thermal energy, our situation doesn't say anything about the temperature changing. The water is at 0 degrees to begin with, so it has low thermal energy to begin with. I'm going to say it has half, because 0 degrees is pretty cold. And all our situation is telling us is that it's freezing. It's changing from a liquid to a solid. So we can assume that our thermal energy hasn't changed. It's still at 0 degrees Celsius. All it's done was make that transition from a liquid to a solid. So in this case, we have 2.5 total, 2-phase, half thermal. And then at the end, we have 1.5. We have 1 phase and half thermal, which means that we lost 1 bar of energy. In this case, we lost 1 bar of phase energy. So in both of these situations, energy left the system. Anytime energy leaves the system, we call that process exothermic. So an exothermic reaction, an exothermic process, is anything that results in energy leaving or exiting a system. So that's the easiest way to remember this. Exothermic means energy is exiting. Exothermic, energy exits. So anytime you have a decrease in energy of your system, anytime energy is leaving, then you know that you have an exothermic process. Both of these first two examples were considered exothermic processes because energy left our system. So let's look at some different situations. Okay, this situation says a can of cold soda warms as it is left on the counter. So if we imagine that we have a can of Diet Coke, that's my preference, Diet Coke sitting on the counter, we forget about it, and it goes from being cold to being warm. First question, has the soda changed states? No. It started as a liquid, it's still a liquid. Hasn't changed state. So I'm going to say that this soda still has 2 bars of phase energy before, because it's a liquid. And I'm going to say that it has 2 bars of phase energy after, because it's still a liquid. It hasn't changed states. Nothing in that scenario said anything about it changing states. Okay, so the change that did happen is that it warmed up. So it started cold. So it has low thermal energy. We're going to say that it has 1 bar of thermal energy. And then it warmed up probably to room temperature, unless you heated it. So I'm just going to say it now has 2 bars of thermal energy because it warmed up. Since the can of soda warmed up, we know that it gained thermal energy. So we went from 3 bars of energy total, 2 phase, 1 thermal, to 4 bars of energy total, 2 phase, 2 thermal. That means we had to have gained 1 bar of, in this case, thermal energy. So in this scenario, energy entered our system. It got added to the system from the surroundings, from somewhere else. Okay, so let's look at another situation. So this scenario says an ice cube melts in a glass of water. Okay, let's look at phase energy first. So an ice cube is a solid to start with, so it's going to have low phase energy. We're going to say it has 1 bar. And if the ice cube is melting, we know that it's going from a solid to a liquid. So it's gaining phase energy. It's going from 1 bar of phase energy to 2 bars of phase energy. Now our scenario doesn't say anything about it substantially warming up. All it's doing is changing from a solid to a liquid. So we can still assume that it's fairly cold, that it has low thermal energy. So in this case, we're going from 2 bars of energy total, 1 phase because it's a solid, 1 thermal because it's cold, to 3 bars of energy total, 2 phase because it's now a liquid, and 1 thermal because it's still cold. Our scenario didn't tell us anything about it warming up. So in this case, we still had to gain 1 bar of thermal energy. We went from 2 total to 3 total. So that means we gained energy from our surroundings. Our system gained energy from our surroundings. Anytime energy enters a system, we call this endothermic. So anytime energy is added to a system, anytime energy enters your system, that situation, that process is called endothermic. So solid to a liquid would be endothermic, liquid to a gas would be endothermic. Anytime things are warming up, those would all be considered endothermic situations. So we have energy entering as endothermic. So that's an easy way to remember this. If energy is entering, it's endothermic. Just like with the other one, if energy was exiting, it's exothermic. So all of our processes can be considered either endothermic or exothermic, simply based on whether energy is entering or exiting our system.